Download this code from codegive.com, link in the description below. False data injection, FDI, attack, a detailed tutorial. False data injection, FDI, attacks are a significant threat to cyber-physical systems, CPS, such as smart grids, water distribution networks, and transportation systems. These attacks exploit vulnerabilities in the data acquisition and control systems to manipulate sensor readings and control signals, potentially leading to operational disruptions, equipment damage, and even safety hazards. This tutorial will provide a comprehensive understanding of FDI attacks, focusing on their principles, construction, and mitigation strategies, along with a practical code example to illustrate the attack. 1. Understanding cyber-physical systems, CPS. Before delving into FDI attacks, it's crucial to understand the architecture and operation of a typical CPS. Physical layer consists of physical components like sensors, actuators, and the environment being controlled, example power grid, water network. Data acquisition system, DAS gathers measurements from sensors and transmits them to the control center. This typically involves sensors measure physical quantities, example voltage, current, flow rate, temperature. Remote terminal units, RTUs, /programmable logic controllers, PLCs collect sensor data, perform local processing, and communicate with the control center. Communication networks, wired or wireless networks, example SCADA protocols like modbus, DNP3, that transport data. Control center receives sensor data, runs state estimation algorithms, makes control decisions, and sends control signals back to the actuators. Key components include state estimator estimates the system state, example voltage magnitudes and angles in a power grid, based on sensor measurements. This is often based on a mathematical model of the system. Control algorithms implement control strategies to maintain stability, optimize performance, or respond to disturbances. Human-machine interface, HMI displays system information to operators and allows them to interact with the system. Actuation layer receives control signals and adjusts physical parameters, example opening/closing circuit breakers, adjusting valve positions. Actuators devices that execute control commands. 2. The core principle of FDI attacks. The fundamental goal of an FDI attack is to inject malicious data into the system without being detected by the state estimator. This is achieved by crafting the attack vector in a way that appears consistent with the system's mathematical model. Here's the general idea. System model the state estimator relies on a mathematical model of the system, represented as Z equals Hx plus E, where Z is the vector of sensor measurements. H is the measurement matrix, relating the state variables to the measurements. This matrix reflects the system's topology and sensor placement. X is the vector of state variables to be estimated. E is the measurement noise, assumed to be random. State estimation the state estimator calculates an estimate of the state variables, x_hat, based on the measurements, z. A common method is weighted least squares, estimation. x_hat equals h caret t asterisk r caret dash 1 asterisk h, caret dash 1 asterisk h caret t asterisk r caret dash 1 asterisk z. Where R is the covariance matrix of the measurement noise. Residual test to detect anomalies, the state estimator calculates the residual. R equals Z, H asterisk X underscore hat. A large residual indicates a discrepancy between the measurements and the estimated state, suggesting a potential error or attack. A threshold tau is set, and if R tau, an alarm is triggered. Asterisk FDI attack asterisk an attacker crafts an attack vector A such that when added to the original measurements, Z, the new measurements, Z underscore A equals Z plus A, still result in a small residual. The crucial condition for an undetectable FDI attack is that the attack vector can be expressed as a linear combination of the columns of the measurement matrix H. A equals H asterisk C, where C is a vector that the attacker chooses. This C will become the error in the state variable estimate. When the attacker injects A into the system, the modified measurements are Z underscore A equals Z plus A equals Z plus H asterisk C. The state estimator then calculates a new estimate. X underscore hat underscore A equals H caret T asterisk R caret dash 1 asterisk H, caret dash 1 asterisk H caret T asterisk R caret dash 1 asterisk Z underscore A equals X underscore hat plus C. The residual becomes R underscore A equals Z underscore A, H asterisk X underscore hat underscore A equals Z plus H asterisk C, H asterisk X underscore hat plus C, equals Z, H asterisk X underscore hat equals R. Notice that the residual remains the same as before the attack. Since R underscore A equals R, the attack is undetectable by the residual test, assuming the original residual was small enough to pass the test. 3. Steps in constructing an FDI attack. 1. Obtain the system model. H. The attacker needs to know the measurement matrix H, which describes the system's topology and sensor locations. This is often the most challenging part, requiring reconnaissance and potentially compromising the system to access configuration data. An attacker might also try to learn the topology through observing the system's behavior over time. 2. Select target state variables asterisk the attacker chooses which state variables, x, to manipulate and by how much. This defines the vector C, which represents the desired change in the state estimate. 3. Calculate the attack vector, A using the chosen C and the measurement matrix H. The attacker calculates the attack vector, A equals H asterisk C. 4. Inject the attack asterisk the attacker injects the attack vector A into the sensor readings by modifying the data transmitted from the sensors to the control center. This can be done by compromising RTUs/PLCs, performing man-in-the-middle attacks on the communication network, or exploiting vulnerabilities in the control center software. 4. Code example, Python with NumPy. This example demonstrates an FDI attack on a simple linear system. Important asterisk this is a simplified example for educational purposes. Real-world CPS are much more complex. Explanation of the code asterisk. 1. System definition asterisk the code defines the number of state variables, n underscore state, and measurements, n underscore measurement. It then defines the measurement matrix H. Crucially, you need to replace this H matrix with the actual measurement matrix of the system you are modeling. The R matrix represents the measurement noise covariance, assumed to be the identity matrix for simplicity. 2. True state and measurements asterisk the code generates a true state vector x underscore true and then calculates the corresponding measurements z using the system model z equals hx plus e. Gaussian noise is added to simulate realistic sensor inaccuracies. 3. State estimation asterisk the code performs state estimation using the weighted least squares, method. It calculates the state estimate x underscore hat and the residual r. 4. FDI attack asterisk. Asterisk the code selects a target underscore state underscore index to manipulate. Asterisk it defines the desired change c_value in the target state variable. Asterisk it creates the vector c with the desired change at the target index and zeros elsewhere. Asterisk it calculates the attack vector a equals h at c. Asterisk it injects the attack vector by adding it to the original measurements, z_attacked equals z plus a. 5. State estimation with attack asterisk the code performs state estimation again, but this time using the attacked measurements z_attacked. 6. Comparison asterisk the code compares the original state estimate with the attack state estimate, showing the change introduced by the attack. It also prints the attack vector a. 7. Detectability asterisk the code compares both the original residual and the attacked residual to a predefined threshold. As the attack vector is specifically designed to create a change in the state variable and no change in the residual, you will see that the injected attack goes undetected. Important considerations asterisk. Asterisk accuracy of the system model. H. The success of an FDI attack heavily relies on the accuracy of the attacker's knowledge of the measurement matrix H. If H is inaccurate, the attack vector A will not perfectly satisfy A equals H asterisk C, and the residual will change, potentially triggering an alarm. Asterisk noise levels asterisk real-world systems are noisy. The higher the noise level, the harder it is to detect anomalies. Attackers must consider the noise characteristics when crafting their attacks. Asterisk dynamic systems asterisk this example considers a static system. In dynamic systems, the state variables change over time. The attacker needs to account for these dynamics when constructing the attack. Asterisk nonlinear systems asterisk many CPS are nonlinear. Linear state estimation methods may not be accurate enough, and attackers need to use more sophisticated techniques to bypass the anomaly detection mechanisms. Extended Kalman filter, EKF, based state estimators are often used in nonlinear systems. FDI attacks on EKF-based systems are significantly more complex, involving approximations of the system Jacobian. 5. Mitigation strategies. Protecting CPS against FDI attacks requires a multi-layered approach. Asterisk data validation asterisk implement data validation checks at the RTUs/PLCs and in the control center. This includes asterisk range checks asterisk verify that sensor readings are within physically plausible limits. Asterisk rate of change limits asterisk check that the rate of change of sensor readings is within expected bounds. Asterisk physical consistency checks asterisk validate that measurements are consistent with physical laws and relationships, example Kirchhoff's laws in a power grid. Asterisk improved state estimation asterisk. Asterisk bad data detection asterisk use more robust bad data detection algorithms that are less susceptible to FDI attacks. Asterisk secure state estimation asterisk explore techniques like robust state estimation or state estimation with Byzantine fault tolerance. Asterisk secure communication asterisk. Asterisk encryption asterisk encrypt communication channels to prevent eavesdropping and data modification. Asterisk authentication asterisk authenticate all devices and users to prevent unauthorized access. Asterisk integrity protection asterisk use message authentication codes, MACs, or digital signatures to ensure data integrity. Asterisk intrusion detection systems, IDS deploy IDSs to monitor network traffic and system logs for suspicious activity. Asterisk topology verification asterisk implement mechanisms to detect changes in the system's topology, example line switching in a power grid, that could indicate an attack. Asterisk moving target defense asterisk employ techniques that change the system's configuration over time to make it harder for attackers to develop successful attacks. This can include dynamically changing encryption keys, communication protocols, or even the system's topology. Physical security protect physical access to critical infrastructure components, such as RTUs/PLCs and communication networks. Resilient control design control algorithms that are robust to data integrity attacks and can maintain system stability even if some sensor data is compromised. 6. Further exploration. Research papers search for research papers on FDI attacks in specific CPS domains, example false data injection attacks in smart grids, cybersecurity of water distribution systems. Security standards familiarize yourself with relevant security standards for CPS, such as NIST Cybersecurity Framework and IEC 62443. Cybersecurity training consider cybersecurity training courses specifically focused on CPS security. Conclusion. False data injection attacks pose a serious threat to the reliability and security of cyberphysical systems. By understanding the principles behind these attacks, their construction, and effective mitigation strategies, engineers and security professionals can better protect critical infrastructure from cyber threats. This tutorial provided a foundational understanding and a practical code example. However, real-world systems are significantly more complex, requiring ongoing research and development to stay ahead of evolving attack techniques. Remember to always adapt the code and security considerations to the specific characteristics of the system you are protecting.